Let's break down how vLLM actually manages GPU memory under their hood. There are three key parameters that control everything. Max model length, in this case 16K 1000 tokens, it's per request context seeing. The maximum number of batch tokens, 12K, so per iteration token budget in a batch. And then maximum number of sequences, which in this case is for its parallel sequence slots, so how many requests we can send to one scheduled batch in the same time. So why 30,000 token can fail and how much chunking can save the day? Let's dive in. First, the KV cage. During inference, every single token in a sequence stores two vectors, a key vector and a value vector. This lives in the GPU memory. As the sequence grows, say from 10 to 100 to 1000 tokens, the KV cage grows linearly. Each new token adds another key value pair that has to stay in GPU memory for the rest of that sequence lifetime. So as we can see here, we are adding more KV cage and we are filling the memory. This happens in self-attention layer of the model, but we don't need to know exactly what is it. This is the core tension in LLM serving. GPU memory is finite, but KV cage keeps growing. Now let's look at the max model length, which is maximum prompt plus output tokens per request. So the request context composition is the prompt tokens, so what we type typically, plus first generated token, and then the generated tokens on the output. And this needs to be lower or equal to max model length. In our case, as we discussed, we have 16K of max model length. And now we'll look at the requests that have 10,000 tokens. A request of 10,000 tokens is well within the 16K token limit. The request is accepted. But watch what happens at 18,000 tokens. It blows right past the limit. The request is rejected immediately. This prevents any single request from consuming all the GPU memory and starving other requests. Now let's look at prefill phase and the decode phase. So in the prefill, we get all the prompt tokens at once. So this is our prompt, combined of multiple tokens, and this is a compute heavy. Why? Because all of this we compute in parallel, because we do a lot of matrix multiplications with the GPU, and this is where the time to first token comes from. So the first token will be here as a G1 when this gets computed. So now if I play it, we see the GPU compute get used and the memory bandwidth not so much. And the decode generates tokens one at a time auto-regressively, and it's memory bound because for each step we need all the tokens that get computed here and all the prefill phase, so the prompt. Now let's play it. And we can see we computed G1, G2, G4, G3, and for G1 we needed all these tokens, then for G2 we needed G1 and all these tokens, and for G3 we needed G2, G1, and all of this. This is what autoregressive means. And this is where intern token latency comes from. So these two phases have completely different resource profiles, and that matters for the scheduling. Now, the maximum number of batch tokens. This is the per scheduler step budget. It controls how many total tokens the scheduler can process in single iteration. Think of it as a throughput cap. If this is set to 12,000 tokens, then in one step the scheduler can batch together requests that total no more than 12,000 tokens. Let's see the animation. So here we get sequence A of 5,000 tokens, then sequence B 4,000, and then sequence C, which is 12,000. And then suddenly you get sequence D. So this will need to wait for the iteration in the scheduler because we achieve the maximum token budget. So this single request will exceed this budget and can't be processed in one single step, which is exactly the failure case we'll see soon and why chunked prefill exists. Now let's explain maximum number of sequence and continuous batching. Maximum number of sequence sets how many sequence can run in parallel. Think of this as slots on the GPU. The key inside is continuous batching, but let's see how first static batching works. So we get 6 requests, and the first ones were because 1, 2, 3, 4, so all our slots in the sequence are filled. And then we also get request 5 and 6, but they need to wait for all of this to finish, because in static batching, we need to wait for the full sequence slots to finish. So as you guess, it's pretty slow. Now with continuous batching, as soon as sequence finishes, the slot is reused. So now let's see. We'll finish one of these requests. So now request 2 is done. So slot is freed immediately. And now the request 5 come into slot 2. So as we see in continuous batching, the slots are freed individually and new requests get filled immediately, so we don't waste the GPU cycles. So this dramatically improves throughput under the load. Now let's look at scheduler policy in vLLM. As we can see, the default one is first come first serve ordering with preemption when GPU memory fills. So we have the queue of requests that we get. So request 1 arrive at 0 seconds, B in 1, C in 2 seconds. And now let's see what happens. So we fill the active GPU slots and we are computing request A, B, C at the same time. And then here we can see the KV cache and GPU memory. So as we compute, the GPU memory gets gradually filled up and it becomes full. Now what happens when it gets full? As we use the first come first serve policy, one of these requests, so the last one that arrived, C at time of 2 seconds, will be preempted, so swapped to the CPU, and we stop using KV data so we can finish the first request. Now when it finishes, the slot 3, so request C, is resumed because we have a free GPU memory and so on. There is alternative policy, which is scheduler policy of priority. So if GPU memory is full, the lowest priority request gets preempted. So as we can see, we have the request 1, which have highest priority, request Y have 5 priority. So we preempted the request Z to finish request X first. Here is a real Taylor case. Imagine Qwen 2.5 vision processing a video. We have 18,000 visual tokens plus 12,000 text tokens, which give us over 30,000 tokens. First check, we check the max model length and we set up 16,000. So it will exceed that and it will get rejected, which will give us error. Then we'll check max number of batch tokens, which is 12,000, but we still try to put 30,000, which is too much, so it will also get rejected. So this is common failures that you get will you set up Docker or vLLM. So you need to know how many tokens you will expect and how many tokens you can batch and so on. And these parameters influence also the memory of the model. Now let's talk about chunk prefill, which is the V1 default version in vLLM. This allows decode priority scheduling plus chunked prefill. So now how it works. For example, the last request, we have 30,000 token requests. It will be split into 8 chunks. But here's the key. Decode requests always get priority. So the request D and E will be processed first. And in each iteration, the scheduler will first batch all the pending decode requests here. And then it will fill the rest with the prefill. So in this case, 10,000 token budget. And then we get another request on decodes, let's say again 2, and we'll fill another C4, 5, 6 to the slot to fill the 12,000 tokens. And then we'll get just the last C7 and C8. So by doing this, all 8 chunks get processed, and decodes process first each step, so it allows us better inter-token latency. This latency is basically the latency when we get the first token from prefill, and then we do decode, so we generate autoregressively token one by one. This measures this latency here, and then prefill fills remaining budget, so we have better GPU utilization. This allows us basically to control if we want better inter-token latency, which is related to decode, or time to first token, which is related to prefill, by setting up the maximum number of batch tokens. So this gives you 2 benefits: better inter-token latency because decodes are never blocked by prefills, and better GPU utilization because compute-bound prefill and memory-bound decode opts to share the same batch. You can tune this to smaller batch tokens, give better inter-token latency. larger budgets will give better time to first token, and so on.